So in this video, we will show you the two sections, that is 5.1 and 5.2. So the first theme is gonna be eigenvalues and eigenvectors. So an eigenvector is the non-zero vector that is R 9. So an example of our eigenvectors is for this matrix that is A equals 3, 8, 0, and 1, minus 1. So in this case, we have to find our eigenvalues. So by doing this, we have to use our formula, that is lambda times y minus a equals 0. So we need to apply this formula to our diagonal matrix. So in this case, we have 3 and minus 1. So we can say that 3 is minus lambda and lambda plus 1. We see these signs transition because minus 1 minus lambda is a addition, so it's a sum, so it's lambda plus 1. So we can say that these are our eigenvalues. So first we have to find them. So in this case, it's just like an x. So we have to put plus 3 to put it equals to 0 and minus 1. So in this case, we can see that our eigenvalues are plus 3 and minus 1. We can see this is a problem for 2 times 2 matrix. So we'll see one for 3 times 3 matrix. So in this case, we have our matrix that is 0, 0, 4, 1, 0, minus 17, 0, 1, 8. In this case, we have to follow the same formula as well. So in our diagonal, it will be lambda, and lambda minus 8. So we can say by multiplying these three, we have lambda cubic minus 8 lambda square plus 17 lambda minus 4. So we have to multiply this so we can factor this equation. So it will be lambda minus 4 times lambda square minus for lambda plus 1 equals 0. So in this case, we have three eigenvalues that it will be lambda equals 4, and lambda equals 2 plus square 3, and it will be as well, but with minus. So this is how we find our eigenvalues. We will see another example so you can have an idea about these problems. So we'll put a simple one so you can have an idea. So we have that our matrix is 1/2, 0, 0, minus 1, 2/3, 0, 5, minus 8, and minus 1/4. So in this case, since we have this lower triangular matrix, we can see that these are 0. By knowing that, we can say that the diagonal doesn't have to put our lambda, so we just go straight to lambda equals 1/2, lambda equals 2/3, and lambda equals minus 1/4. So we can say that probably we will always have 2 or 3 lambdas, but we can also have 1. We can't have more than 3. So this is the way to resolve these eigenvalues and eigenvectors. So the other theme I wanna show you is the diagonalization problems. So these are the diagonalization problems are with the next formulas. So it will be, we have to find our determinant, that in this case it will be A. So we can say that A is equal to our matrix, that will be P inverse P times A, that is our final result of our matrix, and our first matrix, that is the problem. So we have to multiply inverse P times A times P. So this will be equal to our answer, that is our diagonal. So we can say that our matrix in this problem is 1, 1, 0, 1, 0, 2, 0, and minus 2, 1, 2. So in this case, we have to substitute the diagonal, but I won't put all the matrix again, so I will just put lambda minus 1. It looks like an x, but now looks fine. Lambda minus 2 lambda minus 2. So we just put our lambdas in our diagonal like the other problems. We have to find our a values here too. So in this case, it will be 1 and 2. We just have two eigenvalues because these ones are the same. So we have to find our three p's. So our first p, we can infer that it will be p1. So it will be this converted into our problem. So we took the minus 1. So here it will be minus 1. We take our zeros and we leave our 1. We find the other one, that is will be p2. That in this case we're gonna substitute this by 1. So just so you know, we put minus 2 plus 1. That will be this equal to minus 1. 2. So it's 1 minus 2. No, it's 2 minus 1. So in this case, it's gonna be 1. So in this case, we can see 0, 1, 0. And our last p is minus 1, 1, and 1. So we have our three p's. So the next step we have to follow, we just by converting this, we can now apply our p's. So in this case, we have to find this value that is p. So we just add our three p's. There will be minus 1, 0, minus 1, is minus 2, sorry, 0, 1, 1, 1, 0, and 1. Okay. So since we have our p, now we can do our formula here. So we have to also find our inverse p. You can use that by finding by calculation or something, any problem you like. So in this case, we have to substitute our p, also our a. In this case, our a is this matrix times our inverse p that you already have to put it here. So in this case, we can say that our final result is 2, 0, 0, 0, 2, 0, 0, 0, 1. So you can see that by multiplying these matrices, we can have our last matrices. I will show you one more example for diagonalization, because there's not always a 3p matrix. Sometimes we just got 2. So in case we have 2 p matrix, we can't continue with the problem. So I will show you an example of that. So in this case, I will just erase this. So now we put this matrix A equals 1, 0, 0, 1, 2, 0, minus 3, 5, 2. So we'll do our same formula to find our eigenvalue. So in this case, it just will be lambda minus 1, lambda minus 2, and lambda minus 2. So you can get an idea, just ignore this. So it will be just if I put 1, minus 3, 5. I'm just not filling all the metrics. So you can have an idea. We'll put it complete this time. Okay. So now we have to substitute this like the other problem. But in this case, we can see that by substituting 2, we have a 0 in this case and a 0 here. So we know that if we only have 2 P matrix, we can't resolve this problem. So in this case, because we have a matrix that had 3 zeros, we only have 2 P's matrices. So in this case, if we continue our problem, it will be a matrix 3 times 2, and that's something we are not looking for. So in this case, the problem can't be done. So this a type of diagonalization problem. So we only have 2 in this case. I will show you the piece I got. So it's P1 equals to 1/3 minus 1/3 1. And the other P is P2 is equal to 0, 0, 1. So this is all for this video. I hope you enjoyed. You have some implementation about this kind of problem. See you in the next video.